Hi everybody, this is Dr. Nigro with a Physics Fundamentals screencast. This one's going to focus on the trig method for vector addition. For my students, this is more for my honors level classes, but if you're interested, have at it. All right, so let's start with talking about vectors in general. All right, we've done a video that's about the basics of vectors, components, and addition. We've also done a video that looks at right triangles, Pythagorean's theorem, and using sine, cosine, and tangent functions. All right, this video is going to look at the mathematics of adding multiple vectors together, drawing in the resultant, and then using the components of those individual vectors to add together to build that resultant vector for us. All right, so I find that a systematic method to approaching these problems is very useful. So I'm going to walk through those steps for you, and then I have two examples that we can work together. All right, so the first thing you should do when approaching one of these problems is define your vectors. All right, I'm going to talk about a table in a minute, but that's usually what I start. I build a table and I define my vectors right there in that table. And so that means magnitude and the direction of those vectors. All right, once I've defined them, then off to the side, I'm going to set up some axes and I'm going to draw, a sketch of the addition. All right, and remember, we talked about this in an earlier video, but when you add vectors, they need to be tip to tail. So you take the tip of the first vector and you start the second vector's tail at that tip, and you work your way through all of the vectors that you have been given. All right, now this should be on a relative scale. All right, and what we mean by that is you want to make sure that the shorter vectors are shorter and that the longer vectors are longer. All right, it doesn't mean that you need to get out a piece of graph paper and do it that way. This is really more a sketch that we're going to use as we work our way through to make sure that our math is reasonable. All right, so we want it to be on a relative scale, but it doesn't need to be perfect. All right, third, we need to add in our resultant. All right, and remember the resultant connects from our origin. So where we started our very first vector to the tip of our final vector. All right, so again, the resultant is going to connect from the origin of to the tip of our final vector. And we just draw that in as a straight line with an arrow. All right. All right, now for the more mathematical portion. All right, once we've got our vectors defined and our sketch done, we need to break each vector into its components. All right, so in other words, we need the x component and the y component, the horizontal and vertical. All right, I personally, this is where a table is very handy here to keep organized. All right, the other thing to keep in mind here is the signs are really important. All right, remember, if you're on the horizontal axis and you're on the left side, then you're negative. And if you're pointing to the right, you're positive. If you're on the vertical axis and you're pointing up, you're positive. If you're pointing down, you're negative. So it's going to influence the signs of our x and y components. And remember, to find that x component, we're going to take the cosine of our angle theta, and then to find the y component, we'll be taking the sine. All right. Okay. Now, once we've got our components all listed, we're going to add them together. So we're going to add the x components, then the y components. All right. To give us the resultant components. All right, and again, this is where our signs are really, really important, because if we need to have a negative somewhere and we don't, then our components for our resultant aren't going to work out right, and it's going to be a mess. All right, next, we're going to use those resultant components and our favorite theorem, to find the resultant magnitude. All right, so again, r squared equals a squared plus b squared, or in this case, r squared equals x squared plus y squared. All right, and then finally, the last step is to use the inverse tangent function to find theta. All right, remember that inverse tangent looks at the y component divided by the x component, and that's going to give us, whoops, not zero, sorry, theta. Sorry about that. Okay, so again, several steps to work through. Define your vectors, draw a sketch to a relative scale, then draw in your resultant, break each of your components, vectors into their components. I tabled them, you'll see. All right, using our cosine and sine functions, add the components for each direction. So the vertical components with vertical components, the horizontal with horizontal, to yield the resultant's components, all right, the components of the resultant. Then Pythagorean's theorem to find the magnitude of our resultant, and then we end by using the inverse tangent function to find theta. Okay. All right, so let's try one. All right, so here we've got a car driving through Acton. The car will move at 12.5 meters per second at 35 degrees west of north, then turns and goes 8.5 meters per second at 50 degrees north of east. What is the car's resultant velocity? All right, so remember, because this is velocity, we need magnitude and direction. All right, so this is why we also have to find that theta angle, right? We can't just do the magnitude, we got to do both. All right, so like I said above, I like to start these problems with a table. All right, so my table, I define my vectors. So I have two vectors, and then I'm going to add them to get to my resultant. So those are my three vectors. All right, lines. All right, I'm going to have a description of each of these vectors. All right, and then from there, I'm going to have the x component and then the y component. Make this a little bit longer. All right, so this is what my table is going to look like. First, I start by putting in the description. I take that straight out of the information from the problem itself. So I have vector 1 at 8.5 meters per second, and we are at 50 degrees. Oh, sorry, I'm looking at the second one. Well, I can do that. We can just switch them. 50 degrees north of east, and then I have a second vector at 12.5 meters per second at 35 degrees west of north. Okay? All right. My resultant vector, obviously, I'm going to have to figure out. All right, so I've defined my vectors. Now what I'm going to do is draw in some axes. All right, it looks like I'm going to be pointing over to the west. So I'm going to make sure, I'm going to set them up this way. I can always move them if I need to. All right, so, all right, vector 2 is 35 degrees west of north. So that means it's 35 degrees away from my y-axis. So, and it's 12.5. So I'm going to make it something like that. All right, so this is my first vector. And then from there, I'm going to be pointing 50 degrees north of east. So you kind of have to think about a second set of little axes right here. And then this is where my next vector is going to start. And 50 degrees north of east means 50 degrees away from my horizontal axis. So I'm going to point that up a little bit like this, 8.5, so maybe about that long, give or take a little bit. All right, I could be a little off. That might be a little long. Maybe I'll back that up a little bit. All right, we'll know in the end if we made it too much. All right, and so then I've got my vectors in there, now the resultant. So I start at my origin and I go up to the tip of that last one, and that's going to be my resultant. All right, so this is vector 1, this is vector 2, and there's my resultant. So this is my sketch. I mean, we'll see. I mean, we may have to go back in and adjust it a little bit, particularly once we get to the end. All right, now I need to do my component calculations. All right, so I know that x, I'll be looking at the cosine, and then for y, I'll be looking at the sine. All right, so to calculate that x component, I'm going to take that 8.5 and multiply it by the cosine of 50 degrees. All right, And when I do that, oh, wait, I have a problem, right? If I think about that 50 degrees, no, that's okay. That's okay. All right, I plug that in and I get negative, oh, no, not negative, positive 5.5 meters per second. All right, I do the same thing, but plug it in. The 8.5 times the sine of theta will give me the y component, and that works out to be 6.5 meters per second. All right, now the 12.5, the 35 degrees west of north. You have to be careful here. You can plug it in that way, all right, and the numbers that you get out are going to both be positive because it's going to think it's in that northeastern quadrant. Or you can realize that the angle from that, vector all the way to 0 is in fact 125 degrees. And you can plug that in and it will fix your sines for you. It doesn't matter whichever way you choose to do it. All right. You just need to keep in mind that that x component has to be negative because you're in that western quadrant of your plot. All right. So we plug in 12.5 times the cosine of 125 and you get negative 7.2 meters per second. All right, if you plug 12.5 times the sine of 125, then you get 10.2 meters per second. All right, so there are components for each of our vectors that we're working with. Now we've got our resultant. All right, so to get to the resultant components, we're going to add each of these. All right, and that'll give us the components for our resultant. So 5.5 plus negative 7.2, we get negative 1.7 meters per second for the horizontal piece. And then for our y piece, we add 6.5 and 10.2, and we get 16.7 meters per second. All right, so if we look, the x component is negative, so it's definitely going to still be in that western quadrant where we are. The y component is positive, so it'll be on the northern side. So where I've drawn my resultant is probably the right place. I mean, the angle's not going to be perfect, but I think we're pretty good in terms of where it is. All right, so next, we need to figure out what the actual resultant magnitude is, and that's where Pythagorean's theorem is going to come in. So the resultant's magnitude is equal to the square root of the x component squared plus the y component squared. All right, so we plug in negative 1.7 meters per second squared plus 16.7 meters per second squared. All right, and we run that through our calculator, and we should get in the ballpark of 16.8 meters per second. So that's the magnitude, 16.8 meters per second. Now we need to figure out, well, what is the angle from there to 0 or from here to here? And then we list our actual coordinates where we are. All right, so this is where our inverse tangent function is going to come in. All right, so we know that theta is equal to the inverse tangent of our y component divided by our x component. All right, so in this case, that inverse tangent is going to be equal to 16.7 meters per second divided by negative 1.7 meters per second. All right, and we plug that in and we find that theta should be negative 84.2 degrees. All right, so if we go back and look, we'll put that up here. So negative 82.4 is here. It's this piece right here. All right, so we're definitely in the right general area. All right, so we go up and we add that to our 2 degrees, and this is going to be the description of our resultant vector. Okay? All right, so let's try another one. Let's go down here. All right, this time we have finding the displacement of a person who walks through 3 sequential paths on a flat field. First, she walks 25 meters in a direction 49 degrees north of east. Then she walks 23 meters heading 15 degrees north of east. And finally, she turns and walks 32 meters at 68 degrees south of east. All right, so this is a slightly bigger problem. We're actually going to have 3 vectors that we're going to be adding to get to our resultant. All right, now I'm going to use D for displacement here. Normally I would use change in X or change in Y, but it gets a little confusing when we're talking components, so just bear with me. So we're going to have 3 pieces, D1, D2, D3, and together they're going to give us our resultant. All right, so again, I'm going to set up my table. Right now, you don't have to use a table. I just personally find it much more, I guess, easier to keep track of everything. So description of each vector is going to go here. And then I'm going to have a spot for my x component and then a spot for my y component. All right, let's start with the description. All right, this is going to be vector 1. So we have 25 meters, and we're moving at 49 degrees north of east. All right, then we have a second vector where they're moving 23 meters at 15 degrees north of east. And then we have a third vector where we're moving at 32 meters at 68 degrees south of east. So there are 3 pieces. All right, so we're going to need to draw this. All right, now if I'm looking, we're doing a whole lot of northeast with a little bit of southeast at the end. So I think I'm going to start by kind of enlarging that northeast quadrant a little bit. All right, now, of course, you can do that however you like. So I'm going to start at the origin with my first vector. So 25 meters at 49 degrees. So 45, so just a little bit above 45. All right, so this is going to be my D1 vector. All right, then a little bit shorter and definitely shallower at 15 degrees. This is going to be D2. All right, and then we turn and go to the southeast. So we're still moving eastward, but we're going to point that one down at 68. So that's going to be something like this. And it's a little bit longer than my other ones. All right, so this will be D3. All right, then I take my origin and I connect to the tip of my last one for that resultant vector. All right, so this is my sketch. We'll see. We'll see. I may end up below my axis, below in the southern region, but we'll see. We'll have to see. All right, so let's go and do some math. So again, we're going to use the cosine function for our x components and the sine function for our y. All right, so 25 meters times the cosine of 49. All right, that's going to get us 16.4 meters. And the sine version is 18.9 meters. All right, 23 meters times the cosine of 15 degrees is 22.2 meters. And then 23 meters times the sine of 15 degrees is 5.95 meters. All right, then for our last one, this one's a little tricky because it's pointing down, which means that we should have a negative y component. All right, so if we plug it in at 68 degrees, we just need to remember to change that y component sign to negative. Or you can use the angle that wraps all the way around to that vector, which is around 292 degrees. That would work too. All right, but it's going to be 32 meters times the cosine of 68 degrees. It's going to be 12.0 meters. And then the sine of that angle times 32, it's going to come out positive, but we need to list it as negative 29.7 meters because we're down in that southern quadrant. Okay, so we've got all our components in, and now we're going to add them all together to get our resultant components. So we add up our horizontal pieces, and we end up with 50.6 meters. And then for our vertical pieces, we add everything together and negative 4.82 meters. Okay, so I can see right away that my y component is negative, so I actually have my last vector is not long enough. All right, so my last vector needs to end down here. All right, again, I know that because of the negative sign right here. All right, now on an assessment, you just do your best and you do exactly what I just did and you go back and fix it. All right, so there's our resultants actually pointing to the east, but also to the south. All right, so there we go. So that's a better look for our graph. All right, up next, we are going to determine the magnitude of our resultant vector using Pythagorean's theorem. So the resultant displacement is going to be equal to the square root of the x component squared plus the y component squared. So we'll plug those values in. All right, so we have 50.6 meters squared for our horizontal piece, negative 4.82 meters for our vertical piece. Plug in our calculator and we find that the resultant vector has a magnitude of 50.8, and it looks, it's pretty long. meters. All right, so there is the magnitude. Now we end by finding theta. All right, so theta is equal to the tangent inverse of our vertical piece divided by our horizontal piece. All right, in this case, the inverse tangent of negative 4.82 meters divided by 50.6 meters. All right, and we find that theta is going to be equal to negative 5.44 degrees. All right, we are south of east, so you can either say 5.44 degrees south of east, so just barely on the other side of the x-axis, or you can wrap it all the way around from 0 towards 360, and we are at 354.6 degrees. Either will work, all right? And then for our final answer up here, we include both of those pieces, 50.8 meters at 354.6 degrees. All right. Okay, so that's just a couple of examples of how you can use the different steps to work your way through adding vectors and then determining what our resultant vector's magnitude and direction are.